8.3F, we're going to talk about robust procedures and condition adjustments for the t-critical value. Now, when you're doing inference procedures, a procedure is called robust if the probability calculations involved in that procedure remain fairly accurate even when a condition for using the procedure is violated. So let's see how the robust procedures example works. Assume we have this exponential shaped population where the mean of this distribution is at 5. Now we're going to take a random sample of size 5, 15, and 30 from this population and construct confidence intervals for them to see how accurate the confidence intervals are. Let me show you the first results. In this first scenario, we're looking at picking a random sample of 5 elements and computing a confidence interval. Again, the mean of our population was 5, and we took a sample of 5 elements. And what they've done here is you're seeing 100 intervals being computed. We were trying to calculate a 95% confidence interval in this case. So when you look at all of these results, there's 100 results. How many of them are red in that they do not contain the true population mean of 5? What you're going to notice of the 100, only 87% of those truly contain the population mean. Remember, by the definition of confidence level, we want a confidence level of 95%, which means if we do 100 intervals that are created, we should get about 95 of them containing the mean. Here, only 87% of them did. But again, that's with a sample size of 5. Which violates our condition for normalcy because remember, we're looking for a sample size of 30 or higher. So let's increase our sample size from 5 and see what happens. This time we did, again, the mean at 5. We increased the sample size to 15 and we looked at 100 confidence intervals. So here we have our sample size of 15 in all of our intervals. We created confidence intervals with 95% confidence. Now, by increasing the sample size from 5 to 15, instead of 87% of them actually containing the true mean of the population, now 90% of them do. So they're actually getting more accurate. But this still isn't that accurate. Again, our sample size should typically be greater than 30 to do normalcy. Let's go up one. Here we're going to have the same scenario, again our mean, but our sample size is now 30. Here's what 100 intervals look like to be 95% confident. So when the sample size is 30, if you look at all 100 of them, in this case, 94% of them actually contain their true mean, which is very close to us wanting to be 95% confident in our actual level. So we're seeing here, as we increase the sample size, the true definition of our confidence level really does show up more accurately as it should. So really what that analysis tells us is about robust procedures and the fact that large samples improve the accuracy of our critical values. So what we need to recall here is that outliers cause skewness, and they will most impact which statistic? Well, let's take a look at the interval itself that we created. Here's the interval that we created. Remember, outliers are going to have a huge impact on our mean and our standard deviation, which means our interval is really kind of getting screwed up here. So by using this standard deviation, what's happening is T procedures are not robust against outliers and strong skewness. So if you have a sample size less than 30, you have to be incredibly cautious if you have outliers or strong skewness, which is what you're going to see if you were to be drawing from a population that was either skewed to the right, like in this nature, or if it was skewed to the left, like in this picture here. So when the distributions that you're pulling from are skewed right or skewed left, that's when you're going to see those potential outliers or strong skewness. So you have to be careful in those cases because pulling from a skewed right or skewed left distribution will cause your procedures not to be considered robust when you have a sample size of less than 30, which will violate the central limit theorem. Since the T procedures are not robust, we do have to adjust the condition that we check for normalcy. If we have large samples, in this bottom case here, we use T procedures. Even if the population looks skewed, when the sample size is greater than or equal to 30. So we know, even if we're coming from a skewed population or distribution, if our sample size meets this requirement of greater than or equal to 30, we're fine. The central limit theorem says everything is okay. But we have to be cautious for anything under 30. So for this case here, if a sample size has to be up to at least 15, what we have to be cautious of is here. You use T procedures except in the presence of outliers or strong skewness. So what we're looking at is really, in this case, if n is in between 15 and 30. If that happens, we have to kind of go to a different level. You're going to have to graph out your data and look for the presence of outliers and strong skewness. Well, what if you have a sample size less than 15? Sample size is less than 15. In that case, the rule is use T procedures if the data appear close to normal and roughly symmetric with a single peat. Do not use if it's skewed or has outliers. So when you graph the data, and if your sample is less than 15, so in this case if n is less than 15, if you see the skewness or outliers, you technically should not assume the normal condition is met, and you cannot use the T procedures. However, do keep in mind, if the population that we are pulling from is approximately normal, then we can automatically assume that our sample meets the requirements, and we do not have to check any of these T procedure conditions for normalcy. So let's see if the conditions are met for any of these. Determine whether we can safely use a one sample T interval to estimate the population in each of the following. Here in example A, we want to estimate the average GPA of students at your school. We randomly select 50 students from your class, and we see a histogram here of their GPAs at the right. Are we okay with the normal condition being met? Yes, we're okay that the normal condition is being met because this is clearly greater than 30. However, here's where you have to be cautious. Since a sample size of 50 was only from your classes and not from all the students at your school, we should not use the T interval to generalize about the GPA for all the students at the school. Our sample was very much just to our class, so we can only make generalizations about our class because that's the true population. In this case, the design of the confidence interval was not adequately done to know about the entire school, but just from the students from our class. But we're not concerned about the normal condition not being met. We have met it just fine. Part B. The dot plot below shows the amount of time it took to order and receive a regular coffee and 5 visits to a local coffee shop. Sample size is 5, so that's really low. We definitely need to graph it out. If it's less than 30, you have to graph it out. We're looking for any skewness or obvious outliers. Now, in this case, we would say, is the normal condition met? We'd say since the sample size is small and there is a possible outlier, we should not use the T interval. This guy here is pretty far away and could definitely be an outlier, so we should be cautious with this T interval and probably not use it. Letter C. The box plot below shows the SAT math scores for a random sample of 20 students. So now we have 20 students here, which is in between our limit of 15 and 30, so we do need to graph it out. Now we're just looking for the real obvious skewness in here. When you look at this box plot, it looks like it might be slightly skewed to the right, but it's not that bad. What we can conclude here is since the distribution is only moderately skewed and the sample size is larger than 15, it should be safe to use the T interval in this case. So ultimately, this is the one we truly can use the T interval. We know B, we should not use the T interval. A, we can use the T interval, but we have to be careful about our generalization of who our true population is in this case. So I want to take a few moments and highlight the summary of what we learned about the 3 types of confidence intervals in this chapter. Remember to do a confidence interval for the proportion versus one for the mean when you know your standard deviation, and the mean for when you don't know your standard deviation. The parameter of interest you should use in your state component, remember for proportions is a lowercase p, and for the means would be your mu's. Now, when it comes to the plan part, you're going to want to identify what the name of your confidence interval is. Notice for all of these, they're one sample because we're only taking one sample. For the proportion, it's a z-interval. For the means, when you know your population standard deviation, it's a z-interval. When you don't know your population standard deviation, it's a t-interval. And then again, it's the corresponding for the proportion, the mean, or the mean. Now the conditions, they all check for randomness. They all do independence the same way. Remember, you check for independence when you do not do replacement within your study. Now the conditions for normalcy are a little bit unique. For the proportion, remember we are looking that both of these two sets are greater than or equal to 10. Now, if you know your standard deviation of the population, we can go ahead for normalcy and just use the central limit theorem, greater than or equal to 30. Now, because the T procedures are not robust, if you have one that is not greater than or equal to 30, you can still look at it, but you have to test it and look at it different ways. So for greater than or equal to 30, even if the population's skewed, you're fine. Anything greater than a 15 but up to 30, we're looking for no outliers or strong skewness. Anything less than 15, we want no outliers and no skewness whatsoever. Now again, if you actually state the interval itself, you do not have to show these particular formulas on the due portion, but these are the corresponding confidence interval calculations. Remember, for all of these, you do have a calculator method you can use. If you do that, make sure you state the mean and standard deviation for all three. In particular, when you do the t-interval, you must also show your degrees of freedom, which is n-1. And then they all wrap up the exact same way in terms of how we would do the conclusion. Make sure you state it in context, and if you clarify, we're talking about the proportion or the mean. Now remember, at the very beginning of the chapter, we talked about a real-life scenario that might use this confidence interval. And we had a bank manager who wanted to know whether or not the bank's customer service agents generally met their goal of answering the incoming calls within 30 seconds. So we could actually take a sample and compute a confidence interval with a certain level of confidence and see if that 30 seconds is within the realm. That's exactly what they did, and here's how they set up their confidence interval. They wanted to estimate the true proportion, called P, of all the calls to the customer service center that were answered within 30 seconds of the 95% confidence level. So to do that, they're going to do the one sampled z-interval for P. They're going to check for the randomness and realize that they had 241 calls, so it meets that criteria. For the normalcy, when they computed both of these calculations, they both met the requirement of being greater than or equal to 10. For independence, since we are sampling without replacement, there must be at least 2,410 calls in the customer service center. So in the due portion, they computed their p-hat from their sample, and they got this resulting confidence interval. So therefore, they can conclude that they're 95% confidence that the interval from 0.78 to 0.877 captures the actual proportion of calls to the bank's customer service center that were answered in less than 30 seconds. Now, they also had data where they could compute the mean time. So if they wanted to, they could have structured this question to actually estimate the actual mean call response time of the mu and then do a 95% confidence interval. In terms of the checking the plan, in this case, they're going to do a one sample t-interval for mu. We've already checked randomness and independence on the other one. Now, normalcy for this, it's important to see what their population looked like. So what they have here is the histogram at the left and the box plot at the right clearly show the distribution of the call times is somewhat skewed to the right. However, there are no outliers, so based on that, we can rely on the robustness of the T procedures for the inference. And our sample size is 241, so we know that we meet the requirement of greater than 30. Careful here when we do the due portion. We're going to go ahead and do the mean, put this in the confidence interval. We do need to state our degrees of freedom in this case. If we use the calculator for the degrees of freedom, we would just do n-1, or in this case would be 240, which we see right here, and this is the calculator's output. Now, if you did it by hand and use the table, we're going to be conservative because they don't have 240 on the table. The closest smaller number is 100 for degrees of freedom, and then this would be the confidence interval. Based on this, we can say we're 95% confident that this interval stated here actually contains the mean call response time. So in here, you can tell by our analysis that most customers do wait less than 30 seconds based either on the proportion or for our means.